Just picking up on this data, and we're going to do the mini-tab analysis where we assume that tosser is random. It's going to have this one little weird twist in it. So I'm going to go stat, ANOVA, doing my mini-tab thing, and I want to do the general linear model again, fit general linear model. And then the response is going to be the distance from the wall, that's our C4. Our factors are going to be the tosser and the distance. We're not going to do the order yet. We're going to look at that in a hypothetical situation later. But then this is that weird thing that you have, and if you do it on Minitab, you have to go to model, and then you have to get to your interaction term, you have to do one of these at the top, and then the other one at the bottom, and then add that term, add the cross term in, that interaction term in there. So now we've got our model right, just going to go okay. We're going to just do the standard analysis, and now I'm going to go okay, get my output here. All right, and there's my output. All right, we're going to focus in on the the analysis of variance part of it. So this was that weird thing where there was actually, it's really strange that you actually, first the analysis we did before, and we would do the same if we were doing, if we were to think of tosser as a fixed effect, we would do the same kind of thing. We would test the interaction first, follow our same guidelines. If our p-value is more than 0.2, we would probably throw that out and reanalyze the data. But let's not do that right now. And actually, it's weird that your f value is actually even less than 1. So even if something has no effect at all, you'd think on average its f value would be about 1. So this is a little less than you'd expect, even if it has absolutely no interactive effect. Similar thing with the block effect here. But now, if we're thinking of it as a block design, we interpret things a little differently. If you think of it as a block design, then you really only look. Your main thing you're focusing on is the distance, and its p-value is 0.076. So if you thought, if tosser is fixed, you'd say we have. In this case, with the interactive model, we would have not a significant effect of distance. And remember earlier we did toss out that interactive effect, and then we did get a significant distance. But what I'm getting at is the effect of the tosser now. You think of it differently. You're not really worried about are the different tossers different. You'd interpret it like this. You would look at the variability, the variance in the tosser factor, which you could write as like sigma squared sub B, I think. No, it would be sigma squared sub A, I guess we would call that in our notation. That the variance, how much variability there is amongst the different tossers. These three are just three of all the many tossers we could have had. How much do these guys vary? From that we can estimate how much everybody would vary. So things would be a little bit different in this situation here. Now, here's the weird deal though. If, for example, we thought, and probably correctly, we thought that tosser was a random factor, our blocking factor tosser was a random factor, then in that case, it's that weird situation that if you went through your expected mean squares, and because for time considerations, I'm not going to actually go through all those expected mean squares, but the interesting thing is that I'll maybe say briefly that the expected mean squares for tosser, you have more variability in there because you happen to get one set of tossers, but if you got another, they might be different and they might have a different interactive effect with the distance. So in that case, the weird thing is that the expected value for the tosser mean square error is actually a function of sigma squared, the variance of the random error term, but also plus some constant times sigma squared sub AB, the variability of the interaction between tosser and throwing distance, and of course the effect of tosser too, sigma, some function of sigma squared sub, this is first, but I think we call it in the block, we call it sigma squared sub A, I believe. In any case, therefore the appropriate divisor to leave only the increase in variability due to the should be talking about distance now. To talk about the increase in variability in distance would be you'd want to divide by the interaction mean square, because distance is the more the interaction, the more variability you'd get in the distance as well. So in fact, the correct F value would now be the distance mean square divided by the interaction mean square. Let's just say for simplicity that we're going to assume that in these situations where we have multiple observations that that our blocking effect is going to be fixed. In this case, it wouldn't matter because using our rule of thumb, we would throw out this interaction, and therefore we would combine the interaction and the error sum of squares anyways, and so we would do the same test after we went to the reduced model where we took out the tosser and distance. But in general, that's a thing that can happen when you have a mixed model where some factors are fixed and others are random, and you have an interaction term in there. Then it turns out that the one that's fixed, to actually do its hypothesis test, you should do the F from the F by dividing the mean square for your fixed factor divided by the interaction mean square. So it's a weird deal, but we're not going to actually go through the mechanics of that anymore in this class. So, other than that, you can do that same analysis that we did before. But we didn't do a very good design there, if you think about it. If we really thought tosser was a blocking effect, it would make a lot more sense to think about trying to get as much variability into the blocking factor, and that would leave less variability into your treatment factor, or into your error. So in that case, what you might want to do, and also the other thing is that we didn't really incorporate the order at all. But in this one, you could think that you actually would learn this from doing it. So you'd actually think that you would tend to do better in your later tosses than your former tosses. Maybe a little bit by watching other people, but mostly by how you would do it. So in that case, you might want to come up with something that's called a Latin square design. Or actually, in that case, you might want to incorporate order. Well, if you think about it, you have to do this thing called the Latin squares because, the thrower can only have one order. And so it's kind of like splitting units with different orders. And so this is a situation where we're actually might be considering that we have two blocking factors and one treatment factor, and yet you can only do a certain order. So here you might get something like this. I think I'm going to stop this now, and I'm going to pick up on this example on the next movie.